Okay, so I'll talk about a paper recently with Xidong Xialanqi and Shannan Zhou, who's a grad student at Stanford, about the effective entropy of quantum fields coupled with gravity. So the outline of this talk will be mainly three parts. One is talk about the effective entropy proposal, and then talk about a closed universe example. Then the last part will be a tensor network model for a closed universe. So entropy is an interesting subject in a gravitational system. For example, for a black hole, we know that Bekenstein-Hawking entropy give you the coarse-grained entropy of the black hole, which is characterized by the area of the horizon. And in ADS-FT, in holographic system, we know that the Ryu-Takanagi formula tells you the fine-grained entropy of some boundary region. And last year, there have been a new understanding about entropy of ordinary quantum field theory entangled with a gravitational system. So this was expressed in this quantum extreme island formula, where we have quantum field theory region without coupled gravity. We draw A here, and it's entangled with some gravitational system, which is this part. Now the fine-grained entropy of the quantum field theory on region A is given by this quantum extreme island formula, which states that you need to consider possible gravitational regime in the bulk, and then finding the extreme surface, quantum extreme surface, which contains extremize this generalized entropy, which is the entropy of the QFT in A and I, and then plus gravitational entropy on this region I, and you find the minimum of it. So this one gives you the von Neumann entropy of quantum field theory, even if it's not have any gravitational coupling. And apply this rule, give us a page curve. The page curve is a plot of the entropy of the radiation with time. So the Hawking result gives you a growing page curve, and for a unitary system, Page argues that it should turn down because the horizon area shrinks. And the rule can be motivated from double holographic system and can be derived directly from gravity using replica wormholes. And so our first part will just generalize this discussion to situations where gravity is weakly coupled. In other words, we don't want this separation of gravitational system and non-gravitational system. And so our proposal is to define such an effective entropy for a quantum field theory coupled with gravity. Because a priori, you don't know what you are talking about for entropy in a space-time region if gravity is turned on. So our effective entropy proposal states almost the same as the quantum extreme island formula, but you need to talk about some quantum field theory entropy of a matter field in a weakly coupled gravity region. So for ordinary quantum mechanics, we know one way to calculate the von Neumann entropy is through the Renyi entropy formula. So we first study nth Renyi entropy, which is given by n-replica geometry. Yeah, Raphael?
Sorry, just so that the motivation is completely clear, can you tell me why so if I had, before the island formula, if I had worried about the entropy of the room that I'm sitting in,
yeah,
the way that I would have calculated it, I guess, is I would have approximated the geometry of the room as Minkowski space.
And flat.
And used as, that's a fixed background, forgotten about gravity, and just calculated it the usual way in quantum field theory. Yeah. How is this, so just, I know that you're trying to do something more interesting than that, but I think it would help to have that really clear.
Oh yeah, it's not much different from that case. So if there's no like interesting island region up here, so there's no strong QFT entanglement with the other region, yeah, then it will we want this effective entropy to reduce our notion of QFT entropy in a weakly coupled gravity region, the thing you are referring to.
Right, but I don't think you're fundamentally defining it that way, right? And that's
we're not defining it.
Yeah.
But well, there are complaints about whether the page curve calculation really can apply to our universe, and we want to just address that if you use this effective entropy description, which will be the thing you think is quite natural in your mind, then we should also get the page curve. Yeah, so for you, the first part will be very boring, but if you be patient, we'll go to the closed universe, which will be more interesting, I guess. Okay, so we talk about the Rayleigh entropy in quantum mechanics. And so we want to generalize this, to a situation where gravity is turned on. So we want to generalize this formula. And we want to integrate over this formula of a metric. But there are some like technical issues. So for example, here the metric appear both in the denominator and the numerators. Then integrating over, what do we mean by integrating over the metric? And second, to talk about a bulk region, we need to some diffeomorphism invariant way to choose a region A. And third thing is in the QFT, we know that there's a conical angle at the boundary of A. But when gravity is turning on, then gravity wants to smooth out the conical angles. And how do we recover the QFT answer in the limit of G Newton goes to 0? So those are like technical questions, which I will just go one by one to address it. So for example, for the first point, metric appears in the denominator. Here we can apply just a simple trick. We can bring the denominator in the numerator by introducing z to the m, and then take analytic continuation of m goes to minus n. So this is a QFT formula. We can collect it, denote it as have n plus m boundary conditions. And when we come to gravity, we will dealing with this n plus m boundaries. And we couple this n plus m coupled system with gravity. So there will be n plus m metrics. So the second is we need to specify a diffeomorphism invariant way to define this regime. And there are various ways, depends on the situation you want to consider. For example, if there's an asymptotic boundary, then you can refer your bulk regime from the asymptotic boundary. For example, you can say a fixed geodesic distance from the boundary. And in the case without boundary, that's the case we'll discuss later, such as a closed universe, we have a single observer inside the closed universe. And the best thing he can fix is a causal patch. So, so here I'm drawing a single observer. Then in the later discussion for closed universe, we will think about fixing data on a spatial size, and then growing everything outside of the spatial size. Yeah?
I'm confused by how is it easier to define this observer in a diffeomorphism invariant way than defining the surface in a diffeomorphism invariant way?
Oh, so it's not the case as you have an asymptotic boundary. So it's not like you have like if I was like put this way. So in the case with asymptotic boundary, we think about there's a distant star. So we define everything with respect to distant star. But for observer in a closed universe, like what we have now, I'm thinking we define everything with respect to ourselves. We define, so we measured some part, right? We say CMB, we see some part of the CMB. Then we say we define, we just like fix the geometry at that part we observed. And then we'll fill in with smooth geometry compatible with the observation we made. So it's like a different philosophy than Mach principle. It's like based on what we measured locally, and we try to extrapolate what's the global structure of our universe.
Yeah, that makes I think I misunderstood that picture. Sorry.
Yeah. Okay. The third point is the conical deficit. So the replica geometry have conical 2 pi n around the boundary of A. So naively, gravity will smooth out conical angle I just discussed. And in the G-Newton limit goes to 0 limit, we don't recover the QFT answer. And one way we can do this is put a cosmic brane to stabilize the conical angle, such that in the limit of G-Newton go to 0, we recover the QFT answer. And the reason is the following. We should actually, when we're trying to evaluate the Einstein-Hilbert action, we need to be careful about which geometry we should evaluate it. And since we just want to define the entropy for the QFT, the Einstein-Hilbert action should be evaluated on the original untwisted geometry. In other words, the twist operator should only act on the QFT. And then the difference of the gravitational action in the untwisted geometry and twist geometry is exactly this cosmic brane action. So to recover the faithful gravitational path integral, we should by hand subtract out this this cosmic brane action. And then in the limit of G-Newton go to 0, we will recover the original saddle. So we can put them together. So we have n plus m copies of boundaries, which use G tilde to denote the matrix on the twist manifolds. And then we have Einstein-Hilbert action on this twist manifold. Then we put this cosmic brane to return to the, to subtract out these actual contributions. And then we evaluate the QFT entropy action on this gravitational saddle. And when we're evaluating the gravitational path integrals, we might have a topological change. So this gives us some non-trivial saddles in some cases. And then you're using okay, then because this m copies boundary do not have direct coupling with this n copies. So for a wide class, we can think about the leading saddle will factorize. So this not coupled boundary should give you just separate geometries, which is the original saddle, and then this uncoupled geometries, they can have a non-trivial saddles. And with this assumption, we can take the limit of m go to minus n. We can bring this into the denominator. We have this formula. Then applying Lukovic-Madassini argument, we arrive our effective entropy. So that finishes the first part. Are there any questions? What time is it?
It's
how many times do I have?
I'm trying to remember you started. Yeah, I think that you have used 15 minutes.
Okay, good.
Maybe 14 minutes. Yeah.
Okay. Mm-hmm. So the next part is about closed universe, as Raphael has asked. So in this closed universe case, we are imagining we observed some bulk region A, so a space region A. Then we try to guess what the gravitational path integral give us about the information on A. And because we only know the local structures, our best guess is trying, at least for me, seems reasonable. The best guess is trying to find the smooth gravitational saddle without any additional boundary conditions that's compatible with A. So in other words, the density matrix will be described by a summation of all smooth geometries that contains a slit. By slit, I mean I have A and its bra and its bra and ket, A and A prime. A is a bra and A prime is a ket, and then we glue at the boundary of A. This gives us like a bulk region in a closed universe, and then the density matrix should be given by summing over all smooth geometries without additional boundaries. This is like generalization of a Hartree-Hawking state, where Hartree-Hawking, you know the global structure. You assume you know the global structure of the universe. You find your summing of the smooth geometry, and if you only observe like part of the bulk regime, then you're just finding the no boundary geometry for this part of the space-time. And so this is like general procedure. We call this like a slit proposal. And but it's generally hard to realize such proposal. But there's like a special cases one can realize this proposal. This is for example, we can take Euclidean ADS patching function. So the Euclidean ADS, for example, 1 plus 1D. So Euclidean patching function have a circle at the boundary, and then we can flip that we can fold this circle and glue these two half boundaries. And so after this glue, we got a dumpling universe. That's a name suggested by Henry Maxfield when I give a talk at St. Barbara. Because you fold it, you get a dumpling. So it's like a dumpling universe. But anyway, dumpling topologically is a closed universe. So in other words, you treat the Euclidean patching function in the lower half as a bra and upper half as the kit. So for example, you can put, then after you glue these two, you got a closed universe. And because you can specify the operators on these patching functions, you can specify. So this gives you a density matrix on this closed universe on a slit. Well, this is a construction can be constructed in high dimensional Euclidean ADS. You have a patching function, it's manifestly reflection symmetric. You just identify boundaries, which give you a closed manifold. So this is a general construction for to talk about density matrix in a closed universe. And for specific things we can do is in 2D, where we have GT gravity plus CFT. So our gravity description will be 2D GT gravity plus a CFT. And here I draw the red and the blue as a bra and kit. So you can specify the CFT boundary conditions. So this gives you a CFT patching function, but it's a CFT patching function in a closed manifold. The microscopic description will be CFT prepared by a matrix product state. So on this line, there's a Euclidean, you can think about there's a Euclidean SYK evolution. And at the two ends, it's entangled with the SYK. But to talk about the density matrix, we trace out the SYK. And similar construction, not for the density matrix, but just treat this as a wave function, was discussed by Yimin Chen, Victor Gobenko, and Juan Madacena. So here I write down the microscopic description, and in gravity, it's just some path integral. Okay, so we can, for CFT, we do a conformal map. So we fold it, and it's effective a sphere. So it's so for the CFT, its correlators, entropies are effectively those on a sphere, those like on the Hartree-Hawking correlators and entropies, but with like a conformal anomaly, which is like a minor thing. Okay, I may rush a little bit. Are there any questions about this setup? Okay, good. So for example, the correlators, one can calculate it exactly just using conformal transformation from the disk to a sphere. We can find the correlators of this form, where theta is the angle on this boundary. So from 0 to 2 pi. And the beta is a proper length of this boundary. So because it's asymptotic ADS, this beta goes to infinity. And so for fixed proper length, you will find that correlator is of like becomes like vacuum correlators, what we expected. And the entropy of this whole slice of this whole slit is also the CFT entropy. There's a log beta, C times log beta term. where epsilon tilde is a CFT UV cutoff, which is just constant piece. And we see that when C log beta goes to infinity, this naive entropy goes to infinity. But that is just inconsistent with the microscopic description. We have the CFT is just entangled with two SYK systems. So the maximum entropy you can get will be bounded by the SYK, the entropy of the SYK system, which roughly speaking, you can think about is the boundary area. The boundary area of this, the area at the asymptotic boundary. So there's so there should be some something to reduce it, and of course that should be the island. So in this case, we have a slit in a closed inverse. Then there could be an island in the complementary region, and so such island will appear such that when you're calculating the the effective entropy, the von Neumann entropy of the QFT will be bounded by this transverse area at this boundary. So that's a Bekenstein bound. So Bekenstein bound is like generalized Bekenstein bound. It's like some the matter entropy in a gravitational system will be bounded by its boundary area. Here there's the boundary area is phi boundary plus S naught. There's a factor of 2 because I have two boundaries. And the resulting entropy is this like a complicated form, but anyhow, there's you can analyze this thing, and in the limit of large C, the matter field is large, it's almost approach a constant. And the phase transition is happened at this value, where beta times C is order e to the S naught over C. So in this case, we should think about C is order S naught. So it's beta C over phi boundary is order 1. And we can draw a numerical plot. This is a QFT, a naive QFT entropy. This is a contribution from the island. Okay, so that's gravity calculation. I think this gives you like interesting thing about this de Sitter complementary. If it's a de Sitter, here it's not de Sitter, it's just a Euclidean ADS, but it's still some kind of complementarity, where if you know like you have enough entropy in a space-time region you observed, then you can recover what's like the region you outside of your observed region. Okay, so here, this is a gravitational calculation. Are there any questions about this? Okay, I hope I didn't lost everyone. Okay, so the last part is we discuss a random tensor network model for this closed universe. So the random tensor network model is a for the closed universe is constructed the following. So here, this triangle corresponding to a QFT state. So this red lines corresponding to QFT legs. So so if you cut it here, it just gives you some QFT state. So those are the, if you like, it's a qubit, those qubit states. And then this random tensor network model is defined by projecting this QFT states into a random projection. Okay, here this L1, L2 lines, you can think about there's additional EPR pairs, and this random projection is projected at each site. So here is L2 is also some EPR pairs, but with larger bond dimensions. So all of those got projected in. So in total, this closed universe doesn't have any external legs. So there's no legs left open And so if the QFT state is entangled with another system, so here we have a QFT state, then this dashed line is an other system R. So if without this random projection, this described entangled state of R with a QFT. And this random tensor network project all the state on the closed inverse, and this gives you Horowitz-Medicina type of final state projection. You can think about those are this reference state are the Hawking radiations, and this closed inverse is what's behind, what's after fully the inside of the black hole in a fully evaporated black hole system. This random projection is like the final state projection. Okay, so this is what happens if you are an observer who is entangled with a closed universe, who is like not inside of a closed universe. But to make connection with what we have discussed, we want directly an observer inside of this closed universe. Is this tensor network clear? Okay, I guess. So we're trying to introduce observer in this closed inverse. And in tensor network, this can be done by introduce auxiliary system or external observer to couple this CFT in the bulk. And that effectively can be reduced by cutting this legs, this QFT legs. So after you cut it, you have twice the number of states, twice the number of QFT states. You have this A1, which is the original QFT state, but then there's the A2 because you cut it. So the reason why you have this twice number of states is because when you're trying to introduce auxiliary, you want to describe D squared, and D is the dimension of the Hilbert space. You want to describe D squared operators. And then this means that auxiliary need twice number of the qubits of the system you want to describe. And this globally, it's a pure state. So A1, A2 combined is a pure state. And then because A2 and the A2 have a random projection, and this you can just say that the maximum entropy A1 and A2 can get is bounded by this L2, this bound dimension of L2. And that is the same as the Bekenstein-Hawking bound. Okay, so we want to describe the density matrix of A1, so we trace out A2. So trace out A2, give us an analog of the slit density matrix. We have a closed inverse, we only cut it to A1. And we just said that the bound of the entropy were bounded by this boundary area, which is manifest in this tensor network model. And then how about the correlators? For correlators, we have only one copy of this system. So we want to average out this random unitaries. So for random unitaries, I draw this law. If we have V and V star, then on the average, this gives you only one type of contraction, which is like these two legs connected, these two legs connected, and making so for correlators, we want to insert correlators in this on these two legs. So you average these random projections. Then there's only one type of choice. So it's like you're connecting those lines. So after random average, you just get the QFT correlators. That's what you want. So QFT correlators give you the sphere, the Hartree-Hawking correlators. And for random calculations, then it's like basically the same thing. I think someone discussed in the morning. you need to consider additional swap operators between different replica geometries. For example, you have, for the second randomly, you have VV star, VV star. So there's this contractions or this contractions. Translated in this model of closed universe, it means the one contraction will be the same as a QFT entropy calculation. So we still have a sphere topology, and other contraction involve swap operator between these two replicas, were corresponding to a cylinder topology. And that is correct correspondence for the two random geometry for the island. And so depends on the QFT state. So you can have the spherical topology dominates corresponding to without island, or with the quantum extreme island, where in the second random calculation will be cylinder topology dominates. Okay, so in conclude, we discussed three things. One is the effective entropy proposal for bulk quantum fields. We want to relax the condition of QFT. The regime, when you talk about QFT, there shouldn't be any gravity, but we think gravity is weakly coupled is also fine. Then we talk about the Euclidean partitioning function as a density matrix in closed universe. And the last, we talk about a specific random tensor network model for closed universe. Okay, thank you.
Okay, thanks, Zhenbin. We have maybe a few minutes for questions. Few questions.
Okay.
Any questions?
I have a question.
Yeah.
When you want to generalize your slit proposal to time-dependent case, how do you fix the boundary conditions on?
Slit proposal to time-dependent. So here.
Right.
Sorry, can you say your question again?
So when you generalize your slit proposal to time-dependent case, is there something special you have to do?
What do you mean by time-dependent case?
I mean, in the Lorentzian signature.
Oh, yeah. So, okay. So you think about you have like a causal diamond, right? So you have like, so you can fix any spatial size in your causal diamond because those are related by Willard-Witt evolution. So if you want to look at the time dependence, you do just to do another continuation of this slit.
Sorry, is that analytic continuation? I thought that this is like the weight wave function of the universe, because you can have all these possible states and you have a weight. So you just have to introduce clock and you have to see what happens.
Oh, well, yeah, you have like multiple fields, then you have, so to discuss things, you first need to fix your clock, which like, so for example, like infinite field.
Because there is no boundary with respect to which you have a time evolution. So it's just a wave function of the
well,
universe.
Yeah, but yeah, so after you're right.
Okay, if no further questions, let's thanks Zhenbin and all the speakers in the morning.